So still on, we're still on topic 5 for copulas, and the way topic 5 is arranged, I think there aren't actually any exact examples for copulas in topic 5. The examples are moved into topic 6. So in topic 5, we go through the basic notions of a copula. We go through Sklar's theorem, which is very useful for explaining the correspondence there is between how to go from joint distribution to copula and from copula and marginals to joint distribution. And the last part of topic 5 is to talk about how to fit copula to data. And that is what we will do now. So there are two things to consider. The first thing is which type of copula to choose. Which type of copula to choose. And the second thing is to fit. And if we have already chosen a copula, then it's not that hard to fit the copula, because then you just do maximum likelihood estimation of some kind. So the thing that you need to think about is how, like, which type of copula we want to choose. Do we want to choose a Gumbel copula, a Clayton copula, an elliptical copula? Which copula do we want to choose to model our data? And some standard notions that we need to consider when we need to think about this are things such as, well, when we look at, for example, if we plot log returns of one company against the log returns of another company, and we look at how the scatter plot is, then some things that we can think about are stuff like, is there any recognizable pattern, or is there any particular clustering of losses? Well, then if there's something like that, then maybe there is some dependence in the air. Now, some of the notions that we will think about here are things as, for example, symmetry. Can I flip the axes and then still get the same type of joint distribution? Because that will sometimes tell you which type of copula is useful. So symmetry is one thing one can think about. We will not talk about that. The two things that we will talk about are correlation and tail dependence. So what do we mean by correlation? When we talk about correlation, there are normally two notions that we talk about. One is the so-called linear correlation, and the other is what we call rank correlation, which is divided into Kendall's tau or Spearman's rho. And the thing that's quite nice about rank correlation is it is just a measure of concordance versus discordance in your data, and basically the number does not change as long as you apply strictly increasing transformations onto data. So that is a type of correlation which we like to look at, because the correlation translates very well from the original space to the copula space. A kind of correlation that maybe is not that interesting to think about is the linear correlation of the variables in the original space. Since linear correlation is not just a rank correlation, it does not only have to do with whether one variable is smaller or bigger than another. It actually describes very literally whether or not there is linear correlation. So you can often have dependent variables and still a linear correlation of 0. So we're not going to look at this one because it's simply not that relevant in this case. However, we will discuss rank correlation and talk about how the rank correlation in the original space relates to certain things in the copula space. And another thing that we will also talk about is tail dependence. And tail dependence is a measure of whether things get larger together or things get smaller together. We have what we call the coefficient of upper tail dependence and of lower tail dependence. And we will mainly be interested in the coefficient of upper tail dependence. So if this coefficient is positive, then it means yes, the variables do tend to get larger together. If I observe a large value for one variable, it is also quite likely that the other variable has large values. And this is also a phenomenon that is probably more in heavy tail distributions. We do not get this phenomenon in normal distributions. The coefficient of upper tail dependence is always 0 in a multivariate normal distribution. Okay, so now let us look at, or is it always 0? I think it's, now you know what? The thing with the heavy tail and the normal distribution and the 0 and stuff, ignore that. Just the upper tail dependence is normally seen if values tend to get larger together. Okay, so let's start by looking at Kendall's tau. So how is Kendall's tau defined? Let us try to look at the definition of Kendall's tau. So first of all, what I said earlier, that Kendall's tau measures concordance versus discordance. What I mean by that is if data looks like this, then we have concordance, whereas discordance looks something like this. And Kendall's tau is always used to find the rank correlation between two stochastic variables. And the way we do it is we say, well, so for example, if we let x1 model the log returns of one company and x2 model the log returns of another company, and we create an identically distributed copy x1 tilde and x2 tilde, then we define Kendall's tau as the probability that x1 minus x1 tilde multiplied by x2 minus x2 tilde is greater than 0, minus the probability that x1 minus x1 tilde multiplied by x2 minus x2 tilde is smaller than 0. And what this does is, well, in the cases where this first term dominates, it means that it means that if x1 minus x1 tilde is so what am I trying to say? If x1 minus x1 tilde is of one sign, then this tends to have the same sign. So this tends to be negative while this is negative, and this tends to be positive while this is positive. And that is a sign of concordance, whereas the second term models the effect of the discordance. And actually, if the first one here wins, so if this is exactly equal to 1, then we have what we call full comonotonicity, and if this is equal to 1, so if the entire thing is equal to -1, then we have what we call full countermonotonicity. And we also have that when the two stochastic variables are independent, this measure is just 0. The thing that is kind of cool about the Kendall's tau is that it translates very nicely into the copula space. In fact, it is given as 4 multiplied by the mean value of the copula, by the mean value of the copula evaluated in U1, U2 minus 1. So just ignore this stuff. So it translates very nicely into the copula space. And there are specific expressions for this in the case of an Archimedean copula. So we will talk later about what an Archimedean copula is. But anyways, the theoretical value for this for an Archimedean copula is given as 1 plus 4 multiplied by the integral from 0 to 1 of the generating function over the derivative of the generating function dt. So this is for Archimedean copula. And if we want to figure out what Kendall's tau is based on the data, how do we do that? Well, basically what we want is just an empirical estimate of the probability of this thing here being greater than 0 and the probability of another thing being smaller than 0. So we look at all the different ways that we may pick sets of x1, x2, and x1 tilde, x2 tilde out of a sample of n observations. So assume that you have a sample of n observations. Then all in all, you may pick out your pairs in choose 2 ways, right? So I'm just going to write an expression for the estimate for Kendall's tau. And n choose 2 ways. So that is the total number of combinations I have. And what I want to do is I want to count the number of cases where this thing here evaluates to 1, where this thing here is true, and the number of cases where this thing here is true. So I want to count a 1 for each time that x1, so for each time that xj minus, so let's just see if I can get this right. Wait a second. So how do I write this properly? So how do I write this properly? Let's just say that we have n observations, and these are observations of log returns from one company and log returns from another company as such, because this will make our notation easier. So we want to take each combination of differences for log returns of the first company. So it's xij minus xik as such, multiplied by x2j minus x2k, and I want to add these for all the k smaller than j that I find for all my variables. So as such, and then I want to minus all the, so I want this indicator to be 1 if this stuff here is greater than 0. Oh my god, this is such a long expression. And I want the other indicator to be subtracted if I have the case that xj1 minus xk1 multiplied by xj2 minus xk2 is smaller than 0. Okay, so basically the first term is the estimate for this probability, and the second term is the estimate for this probability. I think there must be a nicer way to write this, but this is not necessarily something you need to write up during the exam, I guess. But it's nice just to go through the motions here. So we have the Kendall's tau, and then we have as well something called the Spearman's rho, which is another measure of rank correlation. So we want to look at Spearman's rho, which construction-wise, so how do I write rho? Is this rho? Spearman's rho. So I write rho or rho s. I think we just call Spearman's rho s. Yeah. Okay, so Spearman's rho is defined in more or less the same way as Kendall's tau, actually, except that instead of saying we make an identical copy, x1 tilde, x2 tilde, what we actually do in Spearman's rho is we make 2 identical copies. So what we do is we make one identical copy. So since we're making 2 identical copies, let us just call the first copy y1, y2, and the second copy, z1, z2. So these copies are made so that they have the same distribution as x1, x2. And the thing that we then do is we say, well, what is the probability of x1 minus y1? So for the first coordinate, we compare with the first copy. However, for the second coordinate, we compare with the second copy. So what's the probability of this being greater than 0? Minus the probability of this same thing being smaller than 0. So this is a 1, of this same thing being smaller than 0. And it turns out that due to the way we introduce a new copy, we actually end up with something that's different from Kendall's tau when we translate into the copula space. It's not very different, however. We actually still have a 4 multiplied by the mean value, now just of u1, u2, without evaluating it in the copula. And we have to minus a 1, and we take the entire thing and multiply by 3. Mnemonically, because we have 3 copies. I'm not really sure what the... I mean, we can do the proof and show that this is the case, but the intuitive part of this is maybe best left alone just as such. There is, however, one last thing, which is if I actually go in here and try to break all of this up, then it's actually possible to do some calculations which show that this gives me the linear correlation of u1 and u2 in the copula space, and this is pretty cool. So this is like a pretty cool connection that we can make in the Spearman's row case. And it is also possible to evaluate Spearman's row empirically by using some kind of counting argument, kind of like the one we did above with Kendall's tau. So the last thing we will touch upon in this copula discussion for topic 5 is the notion of tail dependence. So what do I mean by tail dependence? So what do I mean by tail dependence? What I mean by tail dependence is this. So if I just define here the coefficient of upper tail dependence. Then what I mean is I want to look at the probability of so maybe I should just write up lambda u. So the coefficient of upper tail dependence between two stochastic variables x1 and x2. So if I look at the probability of x2 exceeding the a certain threshold, so of x2 exceeding that value of how do I say this? If I look at the probability of x2 entering the top 1 minus u% of its observations, given that x1 enters the top 1 minus u% of its observations, then this probability will tend to something maybe as u goes towards infinity. And if it does converge, then I call this the coefficient of upper tail dependence. So basically what I say is, given that x1 exceeds its u% largest values, what's the probability that x2 exceeds its u% largest values? So note that this limit is defined in terms of each of x1 and x2's distributions. So for x1 this limit may be one thing, for x2 the limit may be another thing. We just know that in both cases the limit is given as the u quantile. Yes. Okay. So how do we look at this when we talk about copula space? So it actually turns out that in terms of uh, of copula notation, this becomes very, very simple, because let's try to write this up. Um, I have u going towards infinity, and the probability of x2 being greater than this value, well, that is just the same as moving this over here. I have a proposition somewhere that allows me to do this, even if f2 isn't continuous, I think. So this is the probability that f2 of x2 exceeds u, given that f1 of x1 exceeds u. And as we know from earlier, if f1 and f2 are continuous, then we have that f2 of x2 is distributed in the same way as u1, and f1 as u2, and f1 of x1 is distributed in the same way as u1. So I have this here. Now, how do I write up this probability? Well, I know that this is equal to the joint probability of u2 being greater than u and u1 being greater than u divided by my conditioned events probability, which is just 1 minus u, since the marginal distribution for u1 and u2, both marginal distributions are standard uniform. So I just need to figure out what the numerator is here, and I can do that pretty easily. I can just write this here. Let's see, if this is the domain of u1 and this is the domain of u2, and I want to look at the probability that both exceed u, then basically what we can notice is I want to find the probability of u1, u2 landing here. And what we can also notice is if I take this thing and add it with this thing and add it with this thing, then I actually get 1 plus this, which is counted twice. So that is 1 plus the probability that u2 exceeds u and u1 exceeds u. So what I get is this is equal to the probability of this plus the probability of this plus the probability of this, and I can move the 1 onto the other side. So this is equal to the probability of u1 smaller than equal to u and u2 smaller than equal to u, plus the probability of u1 being greater than equal to u, plus the probability of u2 being greater than equal to u, minus 1, divided by 1 minus u. Now this is by definition just my copula evaluated in u, and these two are equal to each other and both given by 1 minus u. I should remove this equal sign here, sorry. And this is just a minus 1. So what I get in the end is the tail of upper the coefficient of upper tail dependence is given by CUU plus 1 plus 1 minus 1, so plus 1 minus u multiplied by 2 divided by 1 minus u. And using the same type of reasoning, we may find that the coefficient of lower tail dependence, which is denoted lambda L of x1 comma x2, that is given as the limit for u decreasing to 0. Wait a second. This is just me. I made a mistake here. Sorry. This is for u going to 1. So because u lies between 0 and 1, u is a probability. So this is a 1 here. Okay. So good. So this coefficient of lower tail dependence is the limit for u tending down towards 0 of cu comma u divided by 1 minus u. This is a bit easier to calculate. Okay, so that was the copula stuff, and I guess I'll go on to try and make a 15-minute presentation of this without notes. Not really sure how that's going to work out, but guess we'll see.